Welcome to another exciting educational video brought to you by Vision Concepts Academy. In this video, we'll be looking at mirror equations and calculations. So we're going to be seeing how we can apply some mathematical expressions to curved mirrors. There are formulas, and it's going to interest you. So just stay to the end of the video, and you will see where we can apply the formula. It has been determined in the lab that the image and object and focal length is related with this formula. 1 over u plus 1 over v is equals to 1 over f, where u is the object distance. So object distance, that is distance of the object to the mirror, and v is the image distance, the image formed. Where is it formed and where is the distance from the mirror? And f is the focal length, of the mirror. So the focal length comes with the mirror. So in the lab, they determined that if you plot the graph, of at this axis 1 over u against 1 over v, the graph goes like this. At this point and at this point, they are called intercepts. That intercept is 1 over f. Anywhere it intersects on the axis, it's 1 over f. That is intercept is just between this one and this one. So where it intersects, the distance here is 1 over f, or here 1 over f. So, but how did we come about this formula, or how did we come about this experiment? Where when we finish, we now plot the graph. The thing is that to do this experiment, you only need 3 things. You need your light source. It's not always a pinhole camera. Light source can be a bulb. Use a bulb. Light source. You need your light source. You need what again? You need your screen. It could be a card that has a placeholder on it, just something like this. So you can move this card, and you need the mirror, the curved mirror. Let me just do it like this. So this is a curved mirror. So this is the curved mirror. This is your screen, and this is your light source. So if, for instance, the light source rays beam on this mirror, it reflects and forms image on the screen. Okay, so this is just basically the experiment. So what happens? We'll begin to shift this curved mirror to and fro, so that we can get a distance. We can get a distance where, so this is your light source. So this is the image distance. Sorry, object distance, u. The object reflects into the mirror and forms image. So the image distance is v. So you can just vary it, just shift it a little bit. If you know the focal length of this, you can decide to, focal length is just the length of, where this curved mirror, where all the images converge or diverge. It's a constant. It's a constant on all mirrors. But at the end of the day, we're determining focal length, so we're not even bothered about it. So what I'm trying to say is that this one is, you are shifting it to and fro until you get to a point where you get a sharp image on this screen. That sharp image on this screen, the distance of the object and the image, where you get the first sharp image, you record it. You can just do a table now. I'm just trying to give you a heads up on how the experiment is done. This is u and this is v. The first reading, you take it. Second reading, again, you take it. You just vary until you get when you get a sharp image on this thing, image is formed. If the image is still blurry, you have not gotten your image. There are different positions where you shift this thing. You understand? Where you get sharp image on this screen. The screen might not necessarily be a glass. It can be a cardboard, but the image is formed on it, and you see it there. Okay, so you plot the graph. For the various reading. You plot the graph. You are plotting the inverse of these readings. The inverse 1 over of u and v. Then you get this kind of graph. Okay, so we're going to be looking at sign convention and how to solve mirror equations. Okay, so we have the sign convention on the board. This sign convention is actually used to do calculation. There are two popular conventions. Either you choose this one, the real dispositive convention, or you choose the new Cartesian convention. So for the real dispositive convention, we see that real objects and real images are considered to be at positive distance from the mirror. So when you are calculating, you get your parameters. All real objects and real images are positive distance. You understand? So if you get objects or image distance, it's positive. Then for the new Cartesian convention, distance measured to the right of the mirror is positive. You see this new Cartesian convention, it uses the Cartesian plane. Cartesian plane is like this. Okay, so this is the y, x minus x and plus x. So everything on the right is positive. So if my mirror is here, anything on the right, you understand, it's positive. And anything on the left is negative. That is for new Cartesian. Just anytime you are using this convention, remember the Cartesian plane. Right, positive, left, negative. Okay, so number 2, virtual images for it is positive. Virtual images are negative distance from the mirror. So for the real positive, the first one, real objects, real images are considered to be positive. Virtual images are negative. Sorry, virtual images are at negative distance from the mirror. So when you get virtual images, it's negative. For real is positive, focal length of a concave mirror is positive. And for this one, again, focal length of a convex mirror is negative. So this one is very simple. Real positive, very simple. Real objects, real images positive. Virtual images negative. Concave mirror, focal length is positive. Convex mirror, focal length is negative for real positive convention. Look at that convention. Like I said initially, I said everything to the right is positive. Distances measured to the right of the mirror are positive. So all distances are positive here. Distance measured to the left of the mirror are negative, following the Cartesian plane. Then focal length of it now switch. Focal length of the mirror is negative for concave and positive for convex. So we're going to use this convention to solve some questions. So like the first one I'm going to solve using the two at the same time. No matter the convention you are using, just stick to the rules, you will get the answer. It's the same thing. All right, so let's see. Okay, so we have a question on the board here. It says, an object is placed 10 cm in front of a concave mirror whose radius of curvature is 12. Calculate the position, nature, and magnification of the image produced. So we're going to use two methods. This side will be for real dispositive convention, and this side will be for new Cartesian convention. Okay, so let's go. So okay, I forgot to tell you that the relationship between radius of curvature and focal length is radius of curvature is equals to 2f. So if I have radius of curvature, I want to get my focal length, I will just say r/2 is equals to f. So that's the relationship. Okay, so for this convention, image and object distances are positive. Okay, focal length is also positive. Understand? All right, so let's an object is placed 10 cm. So object distance here, u, is equals to 10. Then radius of curvature, r, is 12. If r is 12, focal length will now be f is equals to r/2, which is equals to what? 12/2, which is equals to 6. Focal length is 6 cm. This one is 10 cm. So calculate the position, nature, and magnification of the image produced. So 1/u plus 1/v is equals to 1/f. So I say real is positive. Everything here is real, positive, right? So I have 1/u. 1/u is giving us 1/10 plus 1/v is what we're looking for. And f is 1/6. Okay. So I'm going to make V subject. So I will say 1 over V is equals to 1 over 6 minus 1 over 10. So I get the LCM of these two. The LCM of these two is 60. So I have 10 here minus I have 6. Okay. Yes. So I have 1 over V here. 1 over V is equals to uh, 4 over 6. So V is actually 15. If V is 15, if V is 15, because we are using the risk positive, the image is also already positive. So we have gotten this image because since V is positive, you understand, the image is what? Real. The image is real. So this is a real image. So I've answered the question, the nature is real image. So for in terms of magnification M is equals to V over U, where V is what? The image distance and U is the object distance. So magnification M is equals to image distance is 15, object distance is 10. M is equals to 1.5. So I've seen that the nature of the image is it is real and it is 15 cm away from the mirror. Magnification is 1.5. That's for the real positive convention. But for the new Cartesian convention, we are told that anything on the right is positive, and anything on the left what is negative. So already, if this one is placed 10 cm in front of the concave mirror, it's on the left. So U here is minus 10, right? Then we have gotten focus as what? Already as 6. But this focus is minus. Why? Because it is the focus of focal length of a concave lens. For Cartesian convention, the concave mirror is minus 6. Why am I calling it lens? Because like I love the lens aspect of optics. We're going to go into lens. Where we see converging lens and diverging lens. So just stay tuned. Subscribe to this channel so that you can be seeing all these videos. I love lenses so much. Understand? So that's why I'm calling lens inside the mirror subject topic. Okay, so this is focal length. Focal length is minus 6 cm. Okay, so we can still apply the same mirror formula, lens formula. 1 over U plus 1 over V is equal to 1 over F. So this 1 over U is 1 over minus 10 plus 1 over V is equal to minus 1 over 6. So by the time this one goes the other way, okay, yeah, so I can say 1 over V is equal to minus 1 over 6 plus 1 over 10. That's it. So by the time I am done, I get V as minus 15 cm. Now, what does this minus tell you in this thing? It tells us that because it is minus for new Cartesian convention, you understand? Minus is on this side, plus is on this side. Minus is on the left-hand side of the Cartesian plane, and plus on the left-hand side. Because it's on the left-hand side of the Cartesian plane, it is real. It is real. Image is real. It is formed on the same side of the object because it's on the left. You know, Cartesian plane is like this. Remember the last what I said before this question. This is minus and this is plus in the Cartesian plane, and the mirror is here. So this minus 15 here tells us that this image is formed on this side, and this side is the same side of the object. Minus. So this image is real. Again, is real. And magnification again is M is equals to minus 15 over minus 10. Say the same thing, 1.5. So whatever convention you use, you can arrive at the same answer. For me, I like using positivity because it makes everything real to me. This one is also easy to use because once you understand Cartesian plane, left and right, positive and negative, you should be able to apply it. But just know the two methods. Okay, we'll go to the next question. All right, so we have a question on the board here. It says an object is placed 15 cm in front of a convex mirror. Always note the kind of mirror you are working with. So the object is placed 15 cm in front of a convex mirror, and an image is produced 5 cm behind the mirror. Calculate the focal length. So I said I love using the real positive. So using the real is positive convention. So what are the key points for this convention? We know that for convex mirrors, every image formed is virtual. So virtual images are negative. Okay, so the object u is equals to 15, that's positive, always positive, and the v is equals to -5, negative, -5, negative. So I apply the mirror formula, 1 over u plus 1 over v is equals to 1 over f. So f I'm looking for. So I say 1 over u is 15, v is -5, that's is equals to 1 over f. So I do my LCM, this is 15 here, 1, and this is 3, minus 1 over, sorry, not minus, please, 1 over f. Okay, so this is minus 2 over 15 is equals to 1 over f. So how do I get f? I just invert. F is equals to minus 15 over 2, which is equals to 7 minus 7.5. So this is the focal length, cm. Focal length is cm. This is the focal length of that mirror. Of course, it is a convex mirror, and that's why it's having that negative sign there. So those signs just tells you the nature. Not specifically just say the magnitude. It's just the nature of that mirror. Okay, so we have a question on the board here. It says a concave mirror of radius of curvature 20 cm produces an inverted image 3 times the size of the object placed on and perpendicular to the axis. Calculate the position of the object and the image. So if I come quickly and just write this formula, mirror formula, 1 over u plus 1 over v is equals to 1 over x. It's called mirror formula here because we're looking at mirror. When we come to lens, we call it lens formula. So this is the mirror formula. So you see that we have to find this and this, and we don't have the two of them, and we don't have f readily. So, but we know that f can be gotten by saying r over 2, where r is the radius of curvature. Radius of curvature is given as 20, right? 20 over 2 will give me 10. So f is 10. So we have 10 now. But we don't have this and this. I said we should find it. But the one that gave us a magnification ratio, it says produces inverted image 3 times. So for magnification formula, m is equals to v over u. We see that 3 here is equals to v over u. And I can express v in terms of u using this formula. I can say v is equals to what? 3u. So I have u is equals to u and v is equals to 3u. So I have these two in terms of u. So I can find u when I put it in this expression. So I come here. I say 1 over u, which is still u, plus 1 over v, which is 3u, is equals to 1 over f. So if I get the LCM, the LCM of these two is what? 3u. U into 3u is 3. 3 times 1 is 3. All right, plus this into this is 1. It's equals to 1 over f. What's f? F is 10 already. So I can put my 10 here. So u is the thing I'm looking for. I'm looking for u. I'm looking for u. Yes. So I have it as 3 plus 1, 4 over 3u is equals to 1 over 10. So this is 40 is equals to 3u. And u is 40 over 3. So I will get it as 13.3 cm. So if I've gotten u, I can put it in this expression to get v. So v is equals to 3 times 13.3. So v now is equals to what? 40 cm. So I've gotten both of them. They are positive. They are positive. They are real images, real image, and this is positive, positive. So this is the answer for this. So I hope you have really enjoyed this video. Thank you for viewing.